All right, in our last video, we talked about half-lives, right? And I brought up the example of the Chernobyl disaster that happened about 34 years ago. And in that video, I mentioned that tens of thousands of people died prematurely due to health effects associated with that disaster. But there were also about 100 people that died within a few weeks of the disaster from acute radiation sickness, which leads to this next video, the health effects of radiation. And it's important to know that high energy radiation is bad for you, right? So high energy radiation can form free radicals. In tissue. Basically what happens is it knocks electrons off of molecules creating unstable/reactive molecules. So a good example of this is if you go out in the sun and you're exposed to a lot of UV radiation from the sun, it'll actually form radicals in your DNA. And what happens is those radicals are so unstable, your DNA will react with itself and cross-link. Now, our body does a pretty good job of having repair enzymes go through and fix all that damage, but the reality is it's not 100% perfect. And if you're exposed to this chronically, over decades and decades and decades, it can cause things like skin cancer or melanoma, right? So that's why I implore people to wear sunscreen as much as possible, and my wife does too. But there's also other things we have to think about with this energy and radiation exposure, right? Let's consider a few different examples. Let's consider an example where we have a large dose and short exposure. All right, so this would be an example like the Chernobyl disaster. The initial firefighters that went in and tried to put out the fire at the reactor site were exposed to a lethal amount of radiation within minutes. It was pretty horrific, and if you go through and watch the HBO series, you can see their agonizing death. It's one of the worst things you could ever die from. But this is just acute radiation sickness. And essentially what happens here is if you're exposed to a massive dose of radiation, it will just kill your tissue, right? So let's imagine your skin cells, right? It's going to kill those skin cells and they won't be able to repair. However, other tissue inside of your body, like your neurons, might be less affected. So if you watch that show, you'll essentially see these people with their skin flaking off and them essentially, this sounds awful, but almost liquefying. That's why we have to keep these reactors behind many, many feet or layers of lead shielding to prevent anybody from being exposed to a massive dose of radiation like this. However, most people would never encounter radiation like this. Instead, the most common exposure is going to be a low dosage. But the problem occurs if you have regular exposure. Right? So this would be an example for healthcare workers, right? If you work in a room where you're taking x-rays all day long, this can also lead to higher rates of cancer. All right, so you might be thinking, well, that doesn't sound good. I want to go into a healthcare field. Isn't there any way I can avoid this? Absolutely. So if you go through the training, you'll see that not only are you not even supposed to be in the room, but the patients that are being exposed to x-rays often are covered in lead shielding. So you might wear a lead bib when you go into the dentist's office to protect you from overexposure. So we want to try to keep our annual exposure below a certain level. The reality is there's always going to be some level of background exposure, and that's fine. I mean, we really can't avoid it by living on planet Earth, but we want to expose ourselves to the least amount possible, which is why you have the lead bib on in the dentist and why healthcare workers normally leave the room when an x-ray is being taken. All right, so let's take a look at this in a little bit more detail. Okay, and what we've got is a list of different effects on the human body, right? So they're measuring it in REMS. We'll go back and we'll talk about that unit a little bit later in another video, but for right now, that's just going to be our unit for exposure, right? So if we get 0 to 25, really no effect, right? I said there's a background amount. Our body does a pretty good job of repairing minor damage. All right, 25 to 100. You get some reduction in blood cells. It's not a huge issue, but it's something you ideally want to avoid as a healthcare professional, right? So wear a lead bib when you get an x-ray or leave the room if you're the person giving the x-rays. 100 to 200, you get nausea and fatigue, potentially vomiting, right? So that's entering the realm of bad stuff. 200 to 300, nausea and vomiting. Recovery is about 3 months. We can typically treat this using special iodine pills to prevent it from all localizing into your thyroid, for example. But even then, it's not the greatest thing to be exposed to. 300 to 600, a good portion of people will die if they're exposed to that level. Some people will live. It's not always clear why some people can be exposed to more and other people less. It's just not something that's well understood. And then 600 or more is near certain death. So yeah, like I was saying, the firefighters and the reactor technicians in Chernobyl were exposed to well above 600, and they got sick within a few hours and then died within a couple of weeks. So pretty tragic stuff right there. All right, but this brings me to my next part, right? Not all radiation is the same. Okay, in the previous videos, I showed you all of the different types of radioactive decay. So let's go back and take a look at this. And we'll focus in on the three main types, alpha, beta, and gamma. Alpha particles really aren't that bad. In fact, if you put up a piece of paper, you can typically stop an alpha particle. It'll just hit the paper and stop, right? And even if you're in air, right, it really doesn't go very far. It goes about 4 centimeters, and that's about it. So that's not to say that alpha particles are safe, right? Because imagine if you ingest it. Well, you've definitely got, tissue within 4 centimeters of whatever you're ingesting, right? So that's not going to be good either. So it's not that it's completely safe, but it's safer than some of the other types of radiation. Beta is kind of second worst. Depending on the tissue, it can go anywhere from, barely into tissue all the way up to about 0.5 centimeter into your tissue. So it goes through tissue a bit better, and it goes much further in air as well. So it is, like I said, substantially more dangerous than alpha particles. And then gamma particles are the really nasty things. These are the ones where we have to use a ton of lead between us and the source to protect us from the gamma rays, right? So if you ever go and tour a nuclear reactor, they have leaded glass where you can actually see the reactor, but the leaded glass is in many cases like a few feet thick. You can still see through that much glass, but it's all leaded glass to prevent any of those gamma rays from coming through. So it is kind of interesting, but all of this depends on the source of emission, right? So it says right here, beta depends on the energy of the rays. So not all of these are going to be exact, it just depends. And then for gamma, the depth is listed to reduce the initial density by 10%, right? So that's why a 30 millimeter lead shielding wouldn't be sufficient enough to protect us from a nuclear reactor. For example, we'd need much, much, much more lead to protect us and keep things safe. All right, that leads me to the next thing. As you can see, distance matters a lot. And this leads to the inverse square law. And this one's kind of interesting. Whoops, I forgot my E there. The inverse square law is this. It says that the intensity of X as a ratio of an intensity to y is equal to the distance squared for y over the distance squared for x. So let's go ahead and label all of these. So this is the intensity. At distance y. ANCE, there we go. This is the intensity at distance x. This is the distance of y, or distance to y, squared, right? And then this is the distance to x squared. All right, so we can say, well, if I'm 5 feet away, I could plug that in here and here, right? And if I'm 10 feet away, I could plug that in here and here. It's an inverse squared relationship. So mathematically, we can determine this. However, this is true for a vacuum. However, we don't live in a vacuum. Most of us live in the air, right? But it's a close approximation for air. All right, so kind of an interesting relationship here, but the moral of the story is radiation drops off pretty quickly with distance. So we don't need to worry about a radiation source if we're relatively far away from it and ideally protected with either lead or some other type of shielding in there. All right, I hope this makes sense and didn't scare you too much. I just really like to emphasize the fact that most of you will be exposed potentially to low dose but regular exposure, whether that's going outside and enjoying the sunshine or working in a hospital where you're using x-rays all day. The key is trying to minimize exposure, right? So if you're going outside into the sun, wear sunscreen. If you're working in a healthcare facility, make sure you follow all of the protocols, including wearing the necessary equipment and or leaving the room if you're administering x-rays. All right, I hope that helps, but let me know if you have any questions.